Agents, your mission to learn and explore the bodacious laws of momentum, work, and energy.
With a weight of 1 kilogram is moving to the right. Its initial speed is 2 meters per second. After traveling 3 meters, it speeds up to 4 meters per second. In addition to the usual force, gravity, normal force, etc., there are 2 forces acting on this box. One is 5 newtons force that has an upward and vertical component of 4 newtons and a component to the left of 3 newtons. The other force is 8 newtons to the right. The normal force is 1 kilogram and the coefficient of the kinetic friction is 1. Springs are pretty darn complicated when it comes to forces. Not only does the magnitude of the spring force vary, the direction of the force depends on whether the spring is being compressed or stretched. As force decreases, simultaneously the position increases.
From the simulation worked by springs, the spring in the 3.2 seconds changed in 3.5 newtons of force and 3.5 points in position.
A mass connected to a horizontal spring sits on a frictionless table. The mass is moved to compress the spring and the system is released from the rest. The energy initially stored in the spring increases and decreases as the spring tied to the object is being pulled and compressed. In the 0.72 seconds, the box slides down the plane. The graphs presented evidence that the potential and kinetic energy are equally associated with the distance of the object, and the mechanical energy was proportionally reflected by the distance.
A simple pendulum is a mass at the end of a light string. If the length of the string is 1.4 meters and the mass is released from rest at a point where the string makes an angle of 20 degrees with the vertical of the maximum speed of the pendulum is about 2 meters per second.
Lesson 5. The block compasses a spring by a length contrasted to the equilibrium length. The spring has a constant. When the block is released, it travels up a slope in comparative distance to the compressed force of the spring. The distance is now taking into account of the usual force, plus the forces of the compressed spring and the friction of the table, to the equilibrium length. The spring has a constant. When the block is released, it travels up a slope in comparative distance to the compressed force of the spring. A mass moving in the x direction at constant speed on a frictionless table is subjected to a force in the y direction, or vertical direction. The force is applied for 0.5 seconds starting at 2.0 seconds. The mass would permanently change the direction at 2.0 seconds.
The elasticity of the collision is related to the ratio of the relative velocities of the two colliding objects after and before the collision.
A ballistic pendulum is a device used to measure the speed of a bullet. A bullet of a certain mass is fired at a block of wood hanging from a string. The bullet embeds itself into the block and causes the combined block plus bullet system to swing up to a height h. The initial speed is the distance the block traveled when shot at and taking into account the mass of the wood. A baseball is placed on top of a basketball and the 2 balls are dropped. When the basketball hits the ground, the baseball shoots up, going much higher than the height it had been dropped from. How can we account for this? The masses of the 2 balls are in roughly a 3-to-1 ratio, which is actually a special case for elastic collisions, as we will see. In the simulation, the baseball is separated from the basketball so that we can analyze the different collisions. Basketball with ground, baseball with basketball, separately. In reality, they take place virtually simultaneously, but the net result is the same. Here we are looking at a collision in 2D, rigid objects. Although we live in a 3-dimensional world, we can think of this 2D example as a special case, where the objects are constrained so that their velocities can be represented in this plane.